Let's learn De Moivre's theorem. With the multiplication of complex numbers, if you have something like cos theta plus I sin theta multiplied by cos theta plus I sin theta, with the multiplication rule, we know that it is cos theta plus I sin theta plus theta, that is equal to cos 2 theta plus I sin 2 theta. Okay, now this left hand side can be written as cos theta plus I sin theta the whole square, because it's the same value, that is equal to cos 2 theta plus I sin 2 theta. Now if you multiply this 3 times, that is cos theta plus I sin theta 3 times, or maybe it is a cube, if it is cube, we are cubing it, you can see that the answer will be cos 3 theta plus I sin 3 theta. So what happens is, whatever value you have here, that will come here and here. Okay, so the generalization of this is De Moivre's theorem. So I can say that cos theta plus I sin theta to the power of n is equal to cos n theta plus I sin n theta. Okay, this is the theorem. This is for all real values of n. This theorem is the combination between complex numbers and trigonometry. Okay, so we have a complex numbers and we are trying to turn it to map it to a trigonometric function with cos and sine. Okay, now let's see how we can prove this. So this proof is a mandatory proof which you have to learn. So the proof has to be done by induction. Okay. And so if you know that proof by induction means that we usually prove it for n is equal to 1, and then you assume it is true for n is equal to k, and then you prove it for n is equal to k plus 1. So this is the normal rule which we use for proof by induction, and I'll create a new video for this explaining the concept of proof by induction, and we're trying some examples. So now we are trying to follow this for this theorem to prove it. So the first step is n is equal to 1. For n is equal to 1, we can say that cos theta plus I sin theta to the power of 1 is equal to cos theta plus I sin theta, which is true. Okay, so the first step is done. Second step is we are assume that it's true for n is equal to k. So I can write that cos theta plus I sin theta to the power of k is equal to cos k theta plus I sin theta. So this is some assumption which we are taking for proving that. The third step is prove it is true for n is equal to k plus 1. So which means that I have to prove that cos theta plus I sin theta to the power of k plus 1 is equal to cos k plus 1 theta plus I sin k plus 1 theta. This is what I have to prove. Okay, now the proof holds. I'm going to take the left hand side. So left hand side is equal to cos theta plus I sin theta to the power of k plus 1, and that can be simplified as cos theta plus I sin theta to the power of k times cos theta plus I sin theta. I'm just splitting this apart. Okay, that is equal to, I'm going to write this from the assumption which we took for n is equal to k. So the equation will become cos k theta plus I sin k theta times cos theta plus I sin theta. Okay, so this is from the assumption. Now what I'm going to do is I'm going to expand this. I'm going to multiply this all together like a normal algebraic multiplication. So I will get cos k theta into cos theta plus I cos k theta into sin theta plus I sin k theta times cos theta plus I square sin k theta sin theta. Okay. Now the second thing what I'm going to do is I square will become minus 1. So this I can change it. This I square I can change it, and this one will become minus sin k theta sin theta. Okay. Now what I'm going to do is I'm just trying to bring this and this together and the imaginary terms together. So what will happen here is cos k theta cos theta minus sin k theta. I'm just rearranging and writing it, okay, plus I times cos k theta sin theta plus sin k theta cos theta. Now if you see this strip, that is nothing but cos a plus b, so it is cos k plus 1 theta. And if you see this section, it is nothing but sin k plus 1 theta. This is from the identities cos a plus b and sin a plus b. So now therefore you need to write, therefore it is true for n is equal to k and n is equal to k plus 1. Okay, so hence we have proved that De Moivre's theorem by induction.